In the name of God, I'm Mohammad Ali Zarif, and we're going to talk about our paper, which is improving performance of multi-label classification using ensemble of feature selection and outlier detection. As you can see, the contents of presentation consist of introduction, related work, proposed method, experimental results, and finally conclusion and future works. So, what's classification? Classification is prediction of label or class of an instance based on previous data. We can categorize classification in two categories: single label classification and multi-label. In single label classification, only one label is assigned to an instance. For example, an apple can only have the apple label. It can't have apple and orange labels at the same time. But in multi-label classification, an instance can have multiple labels at the same time. For example, a movie can have action label and also comedy and drama labels at the same time. As you can see, multi-label classification can be categorized into three categories: problem transformation, algorithm adaptation, and ensemble methods. In problem transformation methods, we transform the problem of classifying multi-label data into another problem in order to solve it. In the first method, in order to improve the performance of chest diseases detection systems, CNN method is combined with problem transformation methods, in which CNN does the feature extraction part and problem transformation methods do the classification part. The next method focuses on finding the relation between labels by finding positive local dependencies between labels. The last method studies the factors which influence the power consumption and battery usage of mobile phones using label power set methods. Algorithm adaptation methods change single label methods so that they can cope with multi-label data and be able to classify them. In the first method, which is based on KNN, in order to classify multi-label data streams, long and short-term memories is used to predict present and future data stream states. The next method uses incremental learning in order to classify multi-label data streams, which uses decremental mechanism. In decremental mechanism, each sample has a weight and this weight decreases as time goes on, which means the focus will be on newer data. Ensemble methods can be created by making a group of classifiers using previous methods. In the first method, a group of classifiers are stacked and weighted in order to create an ensemble. In this method, weights are determined based on the relation between labels and the best members are selected by using an optimization algorithm. In the next method, in order to classify ECG data for detecting heart-related diseases, an ensemble multi-label classifier is applied. This ensemble consists of 7 different classifiers, some of which are binary relevance, ML-TSVM, and ML-Harem. The last method has used CC 4.5 as the base classifier for ensemble of classifier chains method in order to improve the performance of ECC. The goal of our proposed method is the improvement of performance of multi-label classifiers. In order to achieve this, we have proposed an ensemble method, and you can see the structure of it. It has a novel structure which consists of 2 separate ensembles. The whole dataset is given to each ensemble. In each ensemble, the dataset is divided to multiple subsets. One of the ensembles has the task of removing noisy and outlier samples, and the other one has the task of removing redundant and noisy features. In the end, the results of these 2 ensembles are combined together and the output is given to the base classifier. Here we can see how the ensemble with the task of removing outlier and noisy samples works. As we said before, Each ensemble has the whole dataset and it evaluates the performance based on a base classifier and an evaluation metric. After that, the division takes place by randomly dividing the dataset into multiple subsets. Then the performance of each subset is determined based on the base classifier and evaluation metric. If the average performance of the subset is lower than the normal dataset, the division process is repeated. If the performance was better, the next step will be assigning each subset to the root of a tree, and a percentage of the data is removed randomly, which creates a child node. The performance of the created child is evaluated based on the base classifier and evaluation metric. If the performance of the created child is better than its parent, it can create a new child and go to the next level of a tree. And if not, we go back to the parent and other samples are removed randomly, and this process continues until the performance of the created child is better than its parent, or it exceeds the maximum number of created child, which is a predefined parameter. Finally, the stopping condition is checked, which is reaching the maximum predefined tree level. The output will be data without outlier and noisy samples. As mentioned before, the next ensemble has a task of removing redundant and noisy features. Similar to the other ensemble, the dataset is divided to multiple subsets and their performance is evaluated. If the average performance of the subsets has improved, a percentage of the features are removed randomly and a child node is created. The created node is evaluated based on the base classifier and evaluation metric. If the performance of the child is better than its parent, it can create a new child, and if not, we go back to the parent and create another child until the created child has better performance than its parent, or the maximum number of created children is exceeded. Also, the removed noisy features are stored in a list, which will be used later. Finally, the output will be data without noisy and redundant features, and also the list of the removed features. As we mentioned earlier, the removed features are stored in a list. We use that list to remove the noisy features from the output data of the other ensemble, which is data without outlier and noisy samples. So in the end, we will have data without outlier samples or noisy features. Here you can see the datasets used in conducted experiments. All of the used datasets are multi-label datasets, and their domain and other features of them can be seen. Here you can see the methods which have been used as the base classifier. The evaluation metrics used in the conducted experiments can be seen, and their formulas are here. These metrics include Jacquard similarity, accuracy, precision, recall, and F1. The improvement that the proposed method has achieved in different datasets by using various base classifiers can be seen in this table. Also, the Wilcoxon test has been performed and the results are shown in the table. Also, the amount of improvement that the proposed method has achieved has been compared to the amount of improvement that another state-of-the-art method has achieved on the base classifiers shown in the table. And as you can see, our proposed method has shown better improvement in most of the time. As you say, in conducted experiments, the proposed method improved the performance of all the base classifiers and improves the base classifiers more than other state-of-the-art methods. And as for the future works, The proposed method requires some predefined values which can be calculated and optimized in the algorithm by using a multi-objective optimization algorithm. And as you can see, here are the references. And finally, thanks for listening.